All right, today we're going to dig into one of the most influential AI papers from the last few years. Seriously, this thing fundamentally changed how we teach computers to see and understand our world. Okay, let's get right into it. So, it all boils down to this really simple but kind of profound question, right? How do you get a machine, a bunch of code, and circuits to look at a picture of a dog and just know it's a dog? People have been working on this for years, but this paper, well, it carved out a totally new path. Okay, so picture this. What if you could show an AI a picture and just ask it, in plain English, hey, is this a photo of a golden retriever? Or is this the Eiffel Tower at sunset? And it could actually give you the right answer, even if it had never been specifically taught what a golden retriever or the Eiffel Tower was before. That's the kind of magic we're talking about today. Now, to really get why this is such a huge deal, we first have to talk about the old way of doing things and why it was, frankly, hitting a wall. For a long, long time, the way we trained computer vision models was on these huge, meticulously hand-labeled datasets, like the famous ImageNet. Think of it like giving a student a dictionary with exactly 1,000 words. You know, they get really, really good at recognizing those 1,000 things, but that's it. That's all they know. And this is where that old approach started to feel really brittle. So you want your AI to recognize a new breed of dog or a new model of car? Well, you had to start all over again. Collect thousands of new pictures, pay people to label every single one, and then retrain the entire model from scratch. It was painfully slow, super expensive, and just couldn't keep up with the real world. And this is where the paper we're looking at, which introduced the model called CLIP, just completely flips the script. The big idea? Stop using these clean, limited labels and start using the biggest, richest, messiest dataset of all, the internet. You know, this shift in thinking is basically the foundation for so much of the generative AI we see everywhere today. The researchers put together a brand new dataset by scraping a staggering 400 million image and text pairs straight from the web. And we're not talking 400 million images with a single boring label. No, this is 400 million images with their original, messy, descriptive, human-written captions. This whole idea has a name. It's called natural language supervision. Instead of telling the AI, this is category number 234, you're just showing it a picture and the sentence somebody somewhere wrote to describe it. This taps into a way broader, more nuanced world of information than any labeled dataset could ever hope to capture. Okay, so you've got this giant, messy pile of data. Now what? How do you actually use it to teach an AI anything useful? Well, the method they came up with is just brilliantly simple and incredibly efficient. Let's break it down. So instead of making the model do something super hard, like generate the perfect caption for an image from scratch, they gave it a much, much simpler job. In a huge batch of, say, 32,000 images and their 32,000 captions, its only goal was to figure out which image went with which caption. It's basically a massive, massive matching game. So this kind of breaks it down into 3 simple steps. First, the model gets a batch of images and their text captions. Second, it turns both the images and the text into its own special mathematical language. It's like it's building a giant map in its head where similar concepts are placed close together. And then finally, the model learns to tweak that map so that the correct image-text pairs become neighbors and all the wrong pairs get pushed far, far away from each other. And here's the payoff. This contrastive method, this matching game, turned out to be 4 times more efficient with its computing power than trying to predict the text. That boost in efficiency is exactly what made it even possible to train on that insane 400 million pair dataset in the first place. So, what happens when you let a model play this massive matching game for weeks on end with hundreds of GPUs? What did it actually learn? Well, the results were, honestly, they were just astonishing. It developed this incredible ability called zero-shot transfer. Because it learned this general link between pictures and words, it could suddenly classify things it had never, ever been explicitly trained on. You could just give it a totally new set of text labels, like, say, the names of all the dog breeds at a dog show, and boom, it could act as a classifier for them instantly with 0 new training. And I mean, just look at these numbers. On the classic ImageNet benchmark, the best zero-shot model before this had an accuracy of just 11.5%. CLIP came in and scored a whopping 76.2%. This wasn't just a small improvement. It was a totally different ballgame, a complete paradigm shift. But here's the part that really gets me. CLIP, without seeing a single one of the 1.28 million labeled images from the ImageNet training set, performed just as well as a powerful model that was trained on all of them. It didn't just memorize a dataset, it learned to see the world. And this is the conceptual leap that directly leads to things like DALL-E, which use this exact kind of understanding to create images from text. And it learned more than just recognizing objects. The paper shows it picked up a whole bunch of other surprising skills, kind of by accident, just by observing the internet. It learned how to read text in images, that's OCR. It could understand actions. It could even do geolocalization, figuring out where in the world a photo was taken. Now look, any model that learns from the vast, unfiltered internet is, well, a double-edged sword. With all this incredible new power and flexibility comes a whole new set of very serious challenges, and the researchers themselves were actually really careful to explore these. The promise is obvious. You get a more robust, flexible AI that can adapt to new things without needing tons of data. The peril? A model trained on the internet learns from everything, the good, the bad, and the just plain weird. It reflects the data you give it, which means it can absorb all the biases in that data and opens up new ways it could be misused that we have to think about very carefully. And to their credit, the people who made this model were keenly aware of this. Right there in the paper, they report on their own investigations into these problems, stating pretty plainly that they found major disparities in how the model classified people of different races when it was given certain labels to work with. This really gives you a concrete example of how these learned biases can show up. One of their tests found that if you gave the model a set of really problematic, non-human labels as options, it disproportionately applied those labels to images of Black people. It's a really stark reminder of how biases in the data can get learned and then amplified by the model. But this slide reveals something absolutely critical. The user's choices matter a lot. In one test, the model classified young people into crime-related categories way too often. But when the researchers just added the label child as an option, that harmful misclassification rate dropped like a rock. It shows that the very words we choose to prompt the AI with can either trigger or help reduce its hidden biases. And that leaves us with the critical question moving forward, doesn't it? CLIP proved we can teach an AI to see by showing it our world through our language. But as we continue to do that, how do we build in the right guardrails? How do we build systems that can learn from the incredible breadth of human knowledge without also inheriting the worst of our prejudices? That's the challenge this breakthrough leaves for all of us to solve.